Hello, dear cosmic traveling companion. Where are you right now? Perhaps in your bed, wrapped in the softness of sheets, or maybe sitting by a window, watching the stars that are beginning to appear in the evening sky. What time is it there? And how are you feeling today? Is there some restlessness in your heart? Some curiosity whispering in your thoughts? I'd like to invite you on a special journey, a contemplative walk through the cosmos, where we'll explore together one of the most fascinating mysteries humanity has ever dared to investigate. This evening, or perhaps this moment of pause in your day, will be dedicated to something truly extraordinary, the search for other worlds like ours. Close your eyes for a moment and imagine yourself floating gently above Earth. See our blue planet spinning slowly, with its white clouds dancing over the oceans, continents unrolling like a living map of colors and textures. Feel life pulsing in every corner of this world we call home. Now, allow your consciousness to expand beyond Earth's atmosphere, beyond the moon, beyond the familiar planets of our solar system, toward the vast ocean of stars that extends infinitely in all directions. There lies the mystery that will accompany us on this journey. Somewhere out there, orbiting distant stars that shine like diamonds in the darkness, exist other worlds. Worlds that might be surprisingly similar to ours. Rocky planets bathed in the golden light of their suns, with oceans that reflect alien skies, with atmospheres that may harbor the complex dance of life. Have you ever wondered how many of these worlds exist? Have you ever imagined what it would be like to step on the soil of a planet hundreds of light years away? To breathe air that has never been breathed by terrestrial lungs? To contemplate a sky where completely different constellations draw stories we don't yet know? Modern science has brought us revelations that surpass even the most audacious dreams of ancient philosophers. We've discovered that we're not alone in the cosmic sense, not because we found intelligent life, but because we've found places where life, as we know it, could flourish. These are exoplanets, worlds beyond our solar system, and some of them are so similar to Earth that they make us question everything we thought we knew about the uniqueness of our cosmic home. Tonight, or in this moment of quietude, we'll embark together on an exploration that combines the rigor of science with the poetry of discovery. We'll understand how our telescopes have become the eyes through which we can peek at these distant worlds. How scientists decode the language of light to reveal the secrets of planets we can never visit personally, at least not in our lifetimes. Prepare yourself for a journey that will take us from humanity's first questions about the existence of other worlds to the most recent discoveries that are rewriting our understanding of the universe. We'll explore the habitable zone, that special region around each star where water can exist in liquid form. We'll meet planets with poetic names like Kepler 452b, nicknamed Earth's cousin, and Proxima Centauri b, our closest cosmic neighbor. But more than data and discoveries, this is a journey about what it means to be human in a universe that reveals itself each day to be more vast and full of possibilities. It's about our ancestral need to look at the stars and imagine, about our courage to seek answers to questions that have accompanied us since we developed the ability to contemplate the night sky, so settle in comfortably. Let your breathing become slower and deeper. Allow your mind to open to the marvelous, to the impossible that becomes possible through science and imagination. Together, we'll discover what we know about these distant worlds that may be incredibly similar to our cosmic home. And who knows, at the end of this journey, you might feel different when looking at the starry sky, knowing that among those points of light exist planets where alien sunsets paint, horizons with colors that don't yet have names in any earthly language. To truly understand the magnitude of the discoveries we'll make together on this journey, we must first travel back in time, like archaeologists of human thought, excavating the layers of curiosity that brought us here. Have you ever wondered when was the first time a human being looked at the stars and imagined that there could exist other worlds like ours? Imagine yourself in ancient Greece, more than 2,000 years ago. The night air carries the scent of olive trees and the distant sound of the Mediterranean Sea, under a sky without light pollution, where the Milky Way unfolds like a silver river. Philosophers like Democritus already speculated about the existence of infinite cosmoi, countless worlds scattered throughout the cosmos. It was a poetic, almost mystical intuition, but one that carried within it a profound truth that only now, millennia later, we're beginning to fully understand. Epicurus, another thinker of antiquity, wrote that there exist infinite worlds, similar and different from ours. His words echo through the centuries like a prophecy, a seed planted in the garden of human consciousness that would take millennia to germinate and flourish in the form of modern scientific discoveries. But the search for other worlds wasn't just an abstract philosophical curiosity. It was born from something deeper, more visceral, the human need to understand our place in the universe. Are we alone? Is Earth unique, special, or just a grain of sand on an infinite cosmic beach? During the Middle Ages, this curiosity was temporarily stifled by more restrictive worldviews, but never completely extinguished. It was like an ember hidden under ashes, waiting for the right wind to burn again. And that wind began to blow during the Renaissance when Giordano Bruno, the brave Italian monk, dared to proclaim that the stars were other suns, and that around these suns orbited other worlds possibly inhabited. Bruno paid with his life for his revolutionary ideas, burned at the stake by the Inquisition in 1600. But his words survived, planting seeds of curiosity that would continue to grow. Can you imagine the courage needed to defend such a radical idea in an era when questioning Earth's uniqueness was considered heresy? The true scientific revolution came with Copernicus, Kepler, and Galileo. When Galileo pointed his primitive telescope at Jupiter and discovered its moons, something fundamental changed in human consciousness. Suddenly, we were no longer the only system of celestial bodies in the universe. If Jupiter had moons, why couldn't other stars have planets? But discovering planets around other stars would prove to be an almost impossible task with the technology of the time. Imagine trying to see a lit candle next to a powerful lighthouse hundreds of miles away. That's approximately the difficulty of detecting a planet near a star. Planets don't produce their own light. They only reflect the faint light of their host stars, being completely outshone by stellar brightness. For centuries, the search for exoplanets remained in the realm of speculation and dreams. Writers like Voltaire and Fontenelle populated their works with inhabitants of other worlds, feeding the collective imagination. Later, science fiction authors like H.G. Wells and Edgar Rice Burroughs created vivid narratives about Martian civilizations and exotic planets, keeping the fire of popular curiosity alive. But it was only in the 20th century that astronomers began to develop the theoretical and technological tools necessary to transform this millennial search from a dream into rigorous science. Peter van de Camp, a Dutch-American astronomer, dedicated decades of his life trying to detect planets through the astrometry method, measuring the small wobbles that a planet would cause in the movement of its host star. Although his specific claims proved incorrect, van de Camp was on the right track. He understood a fundamental principle. Even if we can't directly see an exoplanet, we can detect its presence through the gravitational effects it exerts on its star. The real breakthrough came in the 1990s, when two groups of astronomers, working independently, developed techniques precise enough to detect the small stellar oscillations caused by orbiting planets. Michel Mayor and Didier Queloz in Switzerland and Jeff Marcy and Paul Butler in the United States were the pioneers who finally opened the doors to the universe of exoplanets. In 1995, Mayor and Queloz announced the discovery of 51 Pegasi b, the first confirmed planet orbiting a sun-like star. It was a strange and unexpected world, a gas giant larger than Jupiter, but orbiting its star in just 4 days, much closer than Mercury is to the Sun. This hot Jupiter challenged all existing theories about planetary formation and showed us that the universe is even stranger and more diverse than we imagined. Can you feel the excitement of that moment? After millennia of speculation, we finally had solid scientific evidence that other worlds exist beyond our solar system. It was as if humanity had, finally, heard a distant echo of its own cosmic voice. Now that we've established the historical roots of our search, let's dive deeper into the fascinating mystery of how we actually detect these distant worlds. Close your eyes again and imagine that you're a cosmic detective, equipped not with a magnifying glass, but with the most sensitive instruments ever created by humanity. The first method that revolutionized our ability to find exoplanets is known as radial velocity, or the Doppler method. It's a technique that explores one of the most subtle dances in the universe, the mutual gravitational influence between a star and its planets. Have you ever watched a couple dancing the waltz? Even when one of the partners is much larger than the other, both move, both respond to the joint rhythm. In space, something similar happens. Although we tend to think that planets simply orbit their stars, the reality is more nuanced and beautiful. Actually, both the star and the planet orbit around a common point called the center of mass or barycenter. For systems where the planet is much smaller than the star, this point lies within the star but still causes a detectable movement. Imagine our own star, the Sun, dancing slowly in space. Jupiter, our largest planet, makes the Sun execute a small circle every 12 years, Jupiter's orbital period. This movement is tiny when seen from afar, but it's real and measurable. If aliens in a distant star system were observing our Sun with sufficiently precise instruments, they could detect Jupiter through this subtle gravitational dance. The genius of the Doppler method lies in how it translates movement into light. When the star moves toward us during its orbital dance, the light it emits becomes slightly bluer due to the Doppler effect, the same phenomenon that makes an ambulance siren sound higher pitched when it approaches you. When the star moves away, its light becomes slightly redder. These changes are incredibly small. We're talking about variations in a star's velocity of just a few meters per second, slower than a leisurely walk. Detecting these minuscule variations in the light of a star light years away is like trying to hear the whisper of a falling leaf amid the roar of a storm. But astronomers develop spectrographs of extraordinary precision, instruments capable of dividing starlight into thousands of component colors and measuring changes in their wavelengths with almost impossible accuracy. It's like having ears so sensitive they can distinguish not just the whisper of the leaf, but the specific sound it makes when touching each different type of surface. The radial velocity method revealed hundreds of exoplanets, but there was an important limitation. It was biased toward detecting large planets close to their stars, because these cause the largest stellar wobbles. It was like trying to study the diversity of ocean fish using only a net that catches only the largest specimens. That's when a second revolutionary technique emerged, the transit method. Imagine you're watching a distant lamp during the night, and occasionally a small moth flies in front of it, momentarily blocking a minuscule fraction of its light. If you knew exactly when to look and had sufficiently sensitive instruments, you could detect these periodic decreases in the lamp's brightness and infer the moth's existence. In the astronomical context, when a planet passes in front of its host star, an event called a transit, it blocks a small portion of the stellar light. For an Earth-sized planet passing in front of a Sun-sized star, the brightness decrease is only 0.008%. Imagine trying to detect the difference between 10,000 lit candles and 9,999.2 lit candles at a distance of several miles. But again, human ingenuity prevailed. Space telescopes like Kepler were designed specifically to monitor thousands of stars simultaneously, looking for these nearly imperceptible periodic decreases in brightness. Kepler was like an extremely patient cosmic fisherman, casting its net into the stellar ocean and waiting years to see what types of planets would be caught. The transit method has a unique advantage. It can detect small, rocky, Earth-sized planets, something that was very difficult with radial velocity. More importantly, when we combine transit data with radial velocity measurements, we can determine both the size and mass of an exoplanet, allowing us to calculate its density and make educated inferences about its composition. Have you ever paused to contemplate the mathematical elegance of this? From small variations in the light of a distant star, we can deduce the existence of an entire world, calculate its size, its mass, its orbit, and even begin to speculate about its composition. It's like being a detective who solves a complex mystery by finding only footprints in the mud. But there's still a third technique that's beginning to bear fruit: direct imaging. This is perhaps the most intuitive of the techniques, simply taking a picture of the planet. But it's also the most technically challenging. Remember the analogy of the candle next to the lighthouse? Now imagine trying to photograph specifically the candle, carefully blocking the lighthouse's light without losing sight of the candle. Astronomers have developed sophisticated coronagraphs instruments that can block a star's light while preserving the much fainter light of any nearby planet. It's a technology that's still in its early stages, but has already produced some of the most impressive images in astronomy. Actual photographs of exoplanets, tiny points of light that represent entire worlds orbiting distant stars. There's something deeply moving about seeing an actual photograph of a planet dozens of light years away. It's no longer just data and graphs. It's a real world, captured by light that traveled through the cosmic void for decades to reach our detectors. Each photon in these images is a messenger that began its journey when you might have been a child, traveling through space to eventually tell its story to our telescopes. Once upon a time, not long ago in cosmic time, but in an era that seems almost mythical now, we launched into space a small observatory with a grand mission to find other worlds like ours. Its name was Kepler, in honor of the great German astronomer who unraveled the laws of planetary motion. And it would forever change our understanding of how common or rare Earth might be in the universe. Can you imagine the excitement of scientists when Kepler was launched in March 2009? It was like sending a tireless explorer to an uncharted region of human knowledge, armed with the most sensitive eyes ever created to detect distant worlds. The telescope was positioned in a special orbit around the Sun, following Earth but gradually moving away, allowing continuous and uninterrupted observations of a specific region of the sky. Kepler wasn't a large telescope by astronomical standards. Its primary mirror was only 95 centimeters in diameter, smaller than many ground-based telescopes. But what it lacked in size, it made up for in precision and dedication. Imagine an observant monk who spent years sitting in silence, meditating on the same view, noticing the smallest changes, the most subtle patterns. That was Kepler's philosophy. The telescope pointed to a single region of sky in the constellation Cygnus, simultaneously monitoring more than 150,000 stars. Every 30 minutes, it measured the brightness of each of these stars with a precision that defies imagination. To give you an idea of the sensitivity required, it was like detecting the decrease in light from a lighthouse when a single ant walks in front of it. For more than 9 years, Kepler carried out this cosmic vigil, accumulating data on planetary transits with a patience that only a machine could have. And what a treasure trove of discoveries emerged from that patience. When the data began to be analyzed, they revealed a universe much richer and more diverse in planets than anyone had dared to imagine. Kepler discovered that planets are not rare in the universe, they are absolutely common. The current estimate, based largely on Kepler data, is that there exists on average at least one planet for every star in the Milky Way. Think about that for a moment. Our galaxy contains about 400 billion stars, which means there could be 400 billion worlds, just in the Milky Way, and there are trillions of galaxies in the observable universe. But Kepler taught us something even more specific and exciting. Earth-sized planets are not particularly rare. The telescope discovered thousands of exoplanet candidates, including hundreds that are classified as super-Earths, rocky planets larger than Earth but smaller than Neptune. Some of these worlds orbit in the habitable zone of their stars, that special region where temperatures allow liquid water to exist on the surface. One of Kepler's most celebrated discoveries was Kepler 452b, quickly nicknamed Earth's cousin by the scientific media. This planet is approximately 60% larger in diameter than Earth and orbits a star very similar to our Sun. Its year lasts 385 Earth days, only 20 days longer than ours. The host star is 6 billion years old, 5 billion years older than the Sun, offering a tantalizing window into what the future of our own solar system could be. Imagine for a moment this distant world. Kepler 452b receives only 10% more energy from its star than Earth receives from the Sun. If it has an atmosphere similar to ours, it may very well have liquid water on its surface. Perhaps it has oceans under alien skies, perhaps clouds that form patterns never seen by terrestrial eyes. If you could stand on the surface of Kepler 452b, you would see a slightly larger and brighter sun than ours, in a sky that may or may not have the same familiar blue color. But Kepler 452b is 1,400 light-years away. This means that the light we see from it today began its journey toward Earth around the year 600 CE, when the Western Roman Empire had already fallen and Europe was entering the Middle Ages. If inhabitants of Kepler 452b were looking in our direction with telescopes similar to ours, they would be seeing Earth from 1,400 years ago. Another fascinating discovery was the TRAPPIST-1 system, although this was confirmed by ground-based telescopes working in conjunction with Kepler data. This remarkable system contains 7 Earth-sized planets orbiting a red dwarf star much smaller and cooler than the Sun. What makes TRAPPIST-1 special is that 3 of these planets orbit directly in the habitable zone of their star. Imagine a solar system where the planets are so close to each other that, if you were on the surface of one of them, you could see the other worlds as clearly visible disks in the sky, perhaps even larger than the Moon appears to us. On TRAPPIST-1 nights, the sky would be dotted not just with stars, but with other worlds, some perhaps showing phases like our Moon, others perhaps displaying distinct surface features. Kepler also taught us about types of planets that simply don't exist in our solar system. It discovered hot Neptunes, Neptune-sized planets orbiting very close to their stars. It found super-Earths, rocky planets significantly larger than Earth but still habitable. It revealed planetary systems with architectures completely different from ours, where giant planets orbit close to their stars while smaller planets remain in the outer regions. One of Kepler's most important lessons was that our solar system is not necessarily the standard model for planetary systems. For centuries, we assumed that other systems would be organized like ours: small rocky planets close to the star, giant gas planets in the outer regions. Kepler showed that this architecture, while not rare, is just one of many possibilities. Perhaps Kepler's most philosophically provocative discovery was what we call the Fulton gap, a curious scarcity of planets with sizes between 1.5 and 2 times Earth's radius. This suggests that there exists some fundamental physical process that determines whether a planet remains rocky like Earth or develops a thick atmosphere like Neptune. It's as if the universe has specific preferences in the manufacturing of worlds. Have you ever wondered if there's something special about Earth's size? Kepler suggested there might be. Planets slightly larger than Earth tend to accumulate very thick atmospheres of hydrogen and helium, becoming potentially uninhabitable mini-Neptunes. Earth may be in a special size range where gravity is strong enough to retain an atmosphere, but not so strong as to accumulate gases that would prevent life from flourishing. But Kepler's legacy goes beyond numbers and statistics. It fundamentally changed our perspective on Earth's place in the universe. Before Kepler, we could speculate that planets were rare, that solar systems were unique, that perhaps we were truly special in the cosmos. After Kepler, we know we live in a universe teeming with worlds, many of which may be surprisingly similar to our cosmic home. While Kepler was revolutionizing our ability to find exoplanets, another marvel of human engineering was being conceived, a successor that would not only find distant worlds, but begin to unravel their most intimate secrets. This is the James Webb Space Telescope, a cosmic cathedral of science and technology that is currently rewriting our understanding of exoplanets and the universe as a whole. Imagine, for a moment, a telescope so sensitive it could detect the heat of a candle on the Moon, so precise it could measure the temperature of a coin from miles away. So sophisticated it can analyze the light from an exoplanet and determine which gases exist in its atmosphere, like a cosmic chemist working with samples from worlds we can never physically visit. The James Webb is not just a bigger telescope than Hubble, it's a complete conceptual revolution. Where Hubble observes primarily invisible light, Webb was designed to see primarily in infrared light, a range of the electromagnetic spectrum that is particularly revealing when it comes to studying exoplanets and their atmospheres. Why is infrared light so important? Think about the sensation of heat you feel when you put your hand near a fire, even without touching it. That heat consists of infrared photons, light that our eyes can't see, but our skin can feel. All objects with temperatures above absolute zero emit infrared radiation, and the amount and characteristics of this radiation tell fascinating stories about the composition and temperature of these objects. In the case of exoplanets, infrared light can reveal not just that a planet exists, but intimate details about its atmosphere. Different molecules absorb and emit infrared light at specific wavelengths like chemical fingerprints, water vapor, carbon dioxide, methane, oxygen. Each of these gases leaves its characteristic mark on light that passes through a planetary atmosphere. Webb's primary mirror is 6.5 meters in diameter, almost 3 times larger than Hubble's, and is composed of 18 hexagonal segments of beryllium covered with a microscopic layer of pure gold. This choice isn't just aesthetic. Gold is the best material for reflecting infrared light, transforming Webb into a golden machine of cosmic discovery. But perhaps the most impressive aspect of Webb is its location. Unlike Hubble, which orbits Earth, Webb was positioned at Lagrange point L2, 1.5 million kilometers from our planet. At this special point in space, Earth's and the Sun's gravity balance in such a way that the telescope can maintain a stable position relative to Earth while both orbit the Sun. This location offers tremendous advantages. Webb is always on Earth's night side relative to the Sun, protected by a tennis court-sized sun shield that keeps its instruments at incredibly low temperatures, about -223 degrees Celsius. This extremely low temperature is crucial because the telescope's own instruments would emit infrared radiation if they were warmer, creating noise that would interfere with observations. Since it began scientific operations, Webb has produced discoveries about exoplanets that were unthinkable just a few years ago. For the first time, we can analyze in detail the atmospheres of planets outside our solar system, detecting not just which gases are present, but also their relative abundances, distributions in the atmosphere, and how they vary with altitude and location on the planet. One of Webb's first groundbreaking discoveries was the detection of water vapor in the atmosphere of WASP 96b, an inflated gas giant orbiting a star 1,150 light-years away. Although this planet is too hot to harbor life as we know it, the clear detection of water vapor definitively demonstrated that Webb could fulfill its promise of revealing the atmospheric compositions of distant worlds. But it was with the study of K2-18b that Webb really began to cause a stir in the scientific community and popular imagination. This exoplanet, located 124 light-years away in the constellation Leo, is about 2.6 times Earth's radius and orbits within the habitable zone of its red dwarf star. Webb detected not just water vapor in its atmosphere, but also carbon dioxide and possibly dimethyl sulfide, a molecule that, on Earth, is produced only by living organisms. Can you imagine the excitement of astronomers when this data was analyzed? It was like receiving a letter from a distant world written in a chemical language we were just beginning to learn to read. Although it's still too early to claim we found signs of life on K2-18b, the detection of these molecules represents a milestone in our ability to study potentially habitable worlds. Webb is also revolutionizing our understanding of how planetary atmospheres form and evolve. By observing young and old planets at different stages of their histories, we're beginning to construct a timeline of atmospheric evolution. It's like being a cosmic archaeologist, excavating the temporal layers of planetary history through chemical analysis of atmospheres. One of Webb's most ambitious projects is the detailed study of the TRAPPIST-1 system. Remember those 7 Earth-sized worlds orbiting a small red star? Webb is systematically studying each of these planets, looking for atmospheres and trying to determine which ones might have conditions favorable to life. The first results are fascinating and somewhat disappointing. TRAPPIST-1b, the innermost planet of the system, appears to have no detectable atmosphere, probably swept away by the intense radiation from its nearby star. But the system's outer planets may still have substantial atmospheres, and Webb will continue studying each of them in the coming years. Perhaps one of Webb's most exciting capabilities is its ability to create rudimentary maps of exoplanets. By observing a planet during its transit, and also when it passes behind its star, the telescope can detect differences in light emitted by different parts of the planet. This allows astronomers to create rough temperature maps, detect the presence of clouds, and even infer wind patterns. Imagine this. We're beginning to do meteorology of worlds hundreds of light-years away. Webb has already detected supersonic winds on some exoplanets, storms that cover entire hemispheres, and temperature gradients that reveal how heat is distributed through alien atmospheres. Have you ever wondered what the weather would be like on a world where one side is always facing its star while the other remains in perpetual darkness? Many exoplanets close to their stars have this characteristic called tidal locking, and Webb is revealing how heat moves between the day and night sides of these worlds. In some cases, Webb has detected atmospheres so efficient at redistributing heat that the night side remains almost as hot as the day side. In others, there are extreme temperature gradients that would create winds of incredible velocities, perpetual storms that would make terrestrial hurricanes seem like gentle breezes. Webb is also teaching us about the chemical diversity of exoplanets in ways we never imagined. It has detected atmospheres rich in vaporized silicates, essentially clouds of sand and molten glass floating in alien skies. It has found worlds where liquid iron reigns and others where diamonds could literally fall from the sky. But beyond these spectacular discoveries about exotic worlds, Webb is increasingly focusing on rocky planets in the habitable zone, the worlds that most resemble our Earth. With each observation, we refine our understanding of what conditions are necessary for a planet to be habitable. A particularly intriguing discovery was the detection of a substantial atmosphere around 55 Cancri e, a super-Earth orbiting very close to its star. For a long time, astronomers debated whether rocky planets close to their stars could maintain atmospheres against intense stellar radiation. Webb confirmed that, yes, at least in some cases, expanding our definition of potentially habitable worlds. The telescope is also beginning to study rocky planets in multiple star systems. Imagine a world where 2 or 3 suns shine in the sky, creating patterns of seasons and climate completely different from anything we know. Webb is revealing that such worlds not only exist, but can be surprisingly stable and even habitable. Perhaps one of Webb's most profound contributions is how it's changing our perspective on planetary habitability. Before its observations, we tended to look for planets exactly like Earth, the same size, at the same distance from sun-like stars. But Webb is showing that habitability can exist in forms we never imagined. Worlds with thicker atmospheres can be habitable even farther from their stars. Planets orbiting red dwarf stars, much smaller and cooler than the Sun, can maintain liquid oceans if they have the right atmospheres. Even moons of giant planets can be habitable if they're in the right zone and have adequate atmospheric protection. There exists a concept in astronomy that captures our imagination like few others: the habitable zone, also known affectionately as the Goldilocks zone, that special region around each star where conditions might be just right for liquid water to exist on a planet's surface. It's an idea that is simultaneously simple and profoundly complex, forcing us to question what it really means for a world to be habitable. Imagine yourself as a cosmic architect, designing ideal conditions for life. What would be your first consideration? Probably temperature, neither so hot as to evaporate all water, nor so cold as to permanently freeze any ocean. This is the essence of the habitable zone, that band of distances where a planet receives enough stellar energy to maintain stable liquid water on its surface. In our solar system, this zone extends approximately from Venus's orbit to slightly beyond Mars's orbit. Earth is perfectly positioned almost at the center of this zone, neither too close to the Sun like Venus, where water vaporizes and escapes to space, nor too distant like Mars, where water freezes permanently in polar ice caps. But have you ever stopped to think about why liquid water is considered so fundamental to life? The answer lies in the unique properties of this seemingly simple molecule. Water is an extraordinary solvent, capable of dissolving an immense variety of chemical substances, creating the perfect environment for the complex biochemical reactions that sustain life. Additionally, water has thermal properties that help regulate temperature. Oceans act as enormous planetary thermal regulators, absorbing heat during the day and releasing it at night. But defining the habitable zone isn't as simple as measuring a planet's distance from its star. A world's actual habitability depends on a complex symphony of factors. A planet's atmosphere, for example, can function as a cosmic blanket through the greenhouse effect, keeping the surface warm even if the planet is technically outside the traditional habitable zone. Venus offers a dramatic example of how atmospheres can dominate planetary temperature. Although it's closer to the Sun than Earth, Venus should have only moderately higher temperatures than ours. Instead, its extremely thick atmosphere, composed mainly of carbon dioxide, creates a runaway greenhouse effect that raises surface temperatures to over 460 degrees Celsius, hot enough to melt lead. On the other hand, Mars demonstrates how the lack of a substantial atmosphere can doom a planet to coldness. Geological evidence suggests that Mars once had oceans and flowing rivers on its surface, but lost most of its atmosphere over billions of years, perhaps due to its weaker gravity and lack of a strong magnetic field to protect it from the solar wind. This leads us to an important realization: the habitable zone isn't fixed in time. It can change as a star ages and becomes brighter, and planets can enter or leave it during their long histories. Our own Earth, for example, was initially outside the habitable zone when the Sun was younger and less luminous. Paradoxically, our planet was habitable at that time because it had a thicker atmosphere that created a stronger greenhouse effect. When we explore exoplanets, we discover that habitable zones around different types of stars have fascinatingly different characteristics. Red dwarf stars, which are smaller and cooler than the Sun, have habitable zones very close to them. Planets in these zones would likely be tidally locked, one side always facing the star. Like the Moon always has the same face toward Earth. Can you imagine what it would be like to live on such a world? One hemisphere in perpetual day, where the Sun never sets, and another in eternal night, where the stars never disappear. Between these extremes, there would be a twilight zone where the Sun would always remain low on the horizon, creating an eternal sunset that could have perfect conditions for life. But red dwarfs present unique challenges for habitability. Many of them are active stars producing intense solar flares that can strip away the atmospheres of nearby planets. On the other hand, these stars live for trillions of years, much longer than stars like the Sun, offering more than enough time for life to evolve and become complex. At the other extreme, we have stars larger and hotter than the Sun. Their habitable zones are wider and more distant. But these stars have much shorter lives. A star twice as massive as the Sun might live only a few billion years before exploding as a supernova, enough time for life to emerge, but perhaps not enough for it to evolve into complex forms. This raises a fascinating question: is there a galactic habitable zone? Some regions of our galaxy might be more conducive to life than others. Too close to the galactic center, cosmic radiation is too intense. Too far from the center, there's a scarcity of the heavy elements necessary to form rocky planets and complex biochemistries. Earth is located in a region that some astronomers call the galactic habitable zone, neither too close nor too far from the Milky Way's center. But perhaps the most revolutionary concept emerging from exoplanet studies is that of superhabitability. Some worlds might be even more suitable for life than Earth itself. Planets slightly larger than Earth might have longer-lasting geological activity, maintaining stable atmospheres for longer periods. Planets orbiting K-stars, slightly smaller and cooler than the Sun, might enjoy stable habitable zones for tens of billions of years. Imagine a world 25% larger than Earth, with deeper oceans, smaller and more fragmented continents, creating longer coastlines where life can diversify, a slightly thicker atmosphere, providing better protection against cosmic radiation, and orbiting a stable K-star. Such a world could be an oasis of life, much richer and more diverse than our own Earth. The concept of the habitable zone is also expanding to include subsurfaces. Moons like Europa and Enceladus, orbiting Jupiter and Saturn respectively, have liquid oceans beneath their ice crusts, heated by energy from gravitational tides. This suggests that habitability can exist far beyond traditional habitable zones, hidden beneath the surfaces of worlds that appear cold and dead on the outside. Some astronomers now speak of circumplanetary habitable zones around giant planets in stellar habitable zones. Moons of these planets could have not just adequate solar energy, but also tidal heating and magnetic protection provided by the giant planet, creating potentially ideal conditions for life. And if we're being even more speculative, we can imagine temporary habitable zones, regions of space that become habitable for limited periods due to cosmic events. A distant supernova could temporarily warm cold planets, creating windows of habitability lasting millions of years. rogue planets ejected from their stellar systems, could maintain subsurface oceans heated by radioactive decay for billions of years. The search for worlds in the habitable zone forces us to confront a profound question. Are we looking for life as we know it, or life as it could be? Our definition of habitability is inevitably based on the only example we know, life on Earth. But the universe may have created forms of life based on completely different chemistries, thriving in conditions we would consider hostile. Have you ever imagined life forms that could prosper in liquid methane atmospheres like those found on Titan? Or organisms that evolved in ammonia oceans under extreme pressures? The traditional habitable zone may be just a small window in a much broader landscape of possibilities for cosmic life. There's something deeply moving about knowing that the potentially habitable exoplanet closest to us is just next door in the cosmic context, at a distance of only 4.24 light-years. Proxima Centauri b, orbiting our nearest stellar neighbor, represents both a fascinating promise and a humbling reminder of how vast the distances in space truly are. To give you perspective on this distance, imagine that our entire galaxy were the size of the United States. On this scale, the distance between Earth and Proxima Centauri would be equivalent to about 4 meters, a short walk. But in reality, even traveling at the speed of light, it would take us more than 4 years to get there. With our current technology, a probe would take tens of thousands of years to complete this journey. Proxima Centauri, the host star, is a tiny red dwarf, only about 12% of the Sun's mass and much less bright. It's so small and faint that, despite being our closest stellar neighbor, it can't be seen with the naked eye from Earth. It's part of the Alpha Centauri star system, a complex gravitational dance involving 3 stars that has fascinated astronomers and dreamers for centuries. The discovery of Proxima Centauri b in 2016 was announced with great fanfare, and for good reasons. Here was a rocky world, with at least 1.17 times Earth's mass, orbiting directly in the habitable zone of its star. Its year lasts only 11.2 Earth days. It's so close to its small, cool star that it completes an orbit faster than some phases of Earth's moon. But you might be wondering, how can a planet so close to its star be in the habitable zone? The answer lies in the peculiar nature of red dwarfs. They're so cool that their habitable zone lies very close to the stellar surface. It's like having a small, weak fire. You need to get very close to feel its warmth. This proximity creates unique characteristics for Proxima Centauri b. The planet is probably tidally locked, meaning the same side is always facing the star, just as the moon always has the same face toward Earth. This would create a fascinating climate pattern, one side of the planet in eternal day, another in perpetual night, and a twilight zone between them where the sun would always be low on the horizon. Imagine what it would be like to be on the surface of Proxima Centauri b. If you were on the day side, you would see a red-orange sun dominating the sky, much larger in appearance than our sun, due to proximity, but emitting softer, redder light. The sky would have a different color, perhaps more pink or orange instead of Earth's familiar blue. On the night side, you would experience a darkness unlike anything known on Earth. Without direct sunlight, the only illumination would come from stars, and what a view that would be. Without light pollution and with a potentially different atmosphere, Proxima Centauri b's night sky could reveal details of the Milky Way. Impossible to see from Earth, the 2 other stars in the Alpha Centauri system would shine like cosmic beacons in the dark sky. But the most interesting zone would be the twilight region, the band between the day and night sides, where the sun would always be rising or setting. Here, temperatures could be more moderate, and if the planet has a substantial atmosphere, powerful winds would transfer heat from the hot side to the cold side, creating unique climate patterns. The question of atmosphere is crucial for Proxima Centauri b's habitability. Proxima Centauri is an active star known for producing intense solar flares. These flares can be hundreds of times more powerful than the strongest flares from our sun. Such radiation bombardment could have stripped away any atmosphere the planet originally possessed, leaving it as an arid, airless world. However, computer simulations suggest that if Proxima Centauri b started with a sufficiently thick atmosphere, it could have retained part of it even after billions of years of stellar bombardment. And if the planet has geological activity, volcanoes, for example, it could be constantly replenishing its atmosphere with new gases. There's also the intriguing possibility that Proxima Centauri b has oceans. If the planet maintained an atmosphere and has the right composition, liquid water could exist on its surface. Some models suggest that even with tidal locking, oceans could efficiently redistribute heat between the day and night hemispheres, creating a more stable global climate. Imagine oceans under a perpetual red sun, with currents following patterns completely different from terrestrial ones due to tidal locking. Perhaps there are permanent ice sheets on the night side that never melt, creating landscapes of indescribable alien beauty. Recently, evidence suggests there may be a second planet in the Proxima Centauri system. Proxima Centauri c, if confirmed, would be a more distant super-Earth, probably too cold for liquid water, but interesting for other reasons. A system with multiple planets around our closest stellar neighbor would be even more exciting, offering comparative laboratories for understanding planetary formation and evolution. But Proxima Centauri b represents something beyond scientific interest. It symbolizes our aspiration to explore other worlds. Several proposals have been made for robotic missions to Alpha Centauri, including the ambitious Breakthrough Starshot project, which aims to send nano-probes propelled by solar sails and powerful lasers to reach the system in just 20 years. Imagine receiving the first direct images of an exoplanet, transmitted across 4.24 light-years of empty space. Even if they were just a few pixels showing variations in color and brightness, they would be the first photographs of a world outside our solar system. We could see seasonal changes, weather patterns, perhaps even signs of an active biosphere. Other nearby star systems also host interesting worlds. Gliese 667c, just 23 light-years away, may have up to 3 planets in the habitable zone. Wolf 359, a red dwarf at 7.9 light-years, has at least 2 known planets. Each of these systems offers a unique window into understanding how planets form and evolve around different types of stars. There's something poetically appropriate about our closest cosmic neighbors hosting potentially habitable worlds. It's as if the universe were inviting us to take the first tentative steps beyond our solar home, offering destinations within the reach, even if only theoretically, of technologies we can imagine developing in the coming centuries. Have you ever wondered if inhabitants of Proxima Centauri b, if they exist, might be looking in our direction? From their perspective, our sun would be a relatively bright star in the constellation Cassiopeia. If they had telescopes like ours, they could detect Earth through transits or other techniques. We would literally be cosmic neighbors observing each other across the interstellar void. The relative proximity of these worlds also forces us to confront fascinating ethical questions. If we develop the ability to travel to other star systems and discover life on Proxima Centauri b, what would be our responsibilities? As cosmic explorers, would we have the right to interfere or colonize? Or would we be morally obligated to remain as silent observers? Proxima Centauri b and other nearby exoplanets represent the first step in a journey that might eventually take humanity to the stars. They are our learning laboratories for detection techniques, atmospheric analysis, and eventually direct exploration. Each discovery brings us closer to answering the fundamental question: are we alone in the universe? There exists a silent symphony being performed in the skies of distant worlds, a complex chemical composition that tells stories about the origin, evolution, and potential future of entire planets. The atmospheres of exoplanets are like cosmic libraries written in molecular language, and we're finally learning to read these extraordinary works. When you breathe right now, you're participating in a chemical miracle that took billions of years to develop. Each oxygen molecule entering your lungs is the product of billions of years of photosynthesis performed by plants, algae, and cyanobacteria. Our air is literally the breath of all life that has ever existed on Earth. It's a realization that changes everything when we begin to analyze the atmospheres of distant worlds. Earth's atmosphere is a complex mixture that tells our planet's story. About 78% is nitrogen, 21% oxygen, and the rest is a collection of trace gases including argon, carbon dioxide, water vapor, and hundreds of other compounds in minuscule concentrations. But it's often these trace gases that carry the most important information about planetary conditions and processes. Oxygen, for example, is highly reactive. Under normal conditions, it would quickly combine with other elements and disappear from the atmosphere. The fact that our atmosphere contains so much free oxygen is an unmistakable signature of life, specifically of photosynthesis. This is why astronomers get so excited about the possibility of detecting oxygen in exoplanet atmospheres. But the atmospheres of other worlds have revealed a diversity that surpasses even our most creative imagination. Some planets have atmospheres composed mainly of hydrogen and helium, like miniaturized versions of Jupiter. Others have atmospheres dominated by water vapor, creating perpetual planetary greenhouses. There are worlds where the atmosphere is so thick that surface pressure would be crushing for any terrestrial life form. HD 189733b, a hot Jupiter 63 light-years away, has one of the most well-studied atmospheres of any exoplanet. This fascinating and terrifying world has winds exceeding 2,000 kilometers per hour, more than 5 times faster than the strongest terrestrial hurricanes. Its atmosphere contains vaporized silicates that condense into clouds of glass, creating rains of glass fragments driven by supersonic winds. Imagine trying to survive in such an environment. The sky would have a deep cobalt blue color, not due to light scattering as on Earth, but because of silicate particles in the atmosphere. Perpetual glass storms would sweep the surface with a force that would reduce any structure to dust in minutes. Other worlds present even more exotic atmospheric chemistries. WASP-121b is so hot that it has vaporized iron and magnesium in its upper atmosphere. As these metals condense at lower altitudes, they create metallic clouds that literally rain liquid iron. It's an extraterrestrial hydrological cycle where metals take the place of water. But perhaps the most intriguing worlds are those that could have habitable atmospheres. K218b, which we mentioned earlier, not only has water vapor detected in its atmosphere, but also shows signs of dimethyl sulfide, DMS. On Earth, DMS is produced almost exclusively by living organisms, particularly marine phytoplankton. The detection of DMS on K218b doesn't prove the existence of life, but it's certainly suggestive. The method by which we detect these atmospheric compositions is in itself a marvel of human ingenuity. When an exoplanet transits in front of its star, a small portion of the stellar light passes through the planetary atmosphere before reaching us. Different molecules in the atmosphere absorb light at specific wavelengths, creating absorption lines in the star's spectrum. It's like analyzing shadows cast by a window with colored glass. Each color of glass blocks certain colors of light, creating a unique pattern of shadows. Similarly, each molecule in an exoplanet's atmosphere creates a unique absorption pattern that we can detect and decode. This technique, called transmission spectroscopy, requires extraordinary precision. We're measuring changes in stellar light on the order of parts per million, like detecting the decrease in light from a lamp, when a single hair passes in front of it at a distance of several rooms. But when we succeed in decoding these spectra, the revelations are spectacular. We can not only identify which gases are present, but also their relative abundances, their distributions in the atmosphere, and how they vary with altitude and location on the planet. TOI 715b, recently discovered, exemplifies how these atmospheric analyses are becoming more sophisticated. This planet, slightly larger than Earth and orbiting in the habitable zone of a nearby red dwarf, shows signs of a substantial atmosphere with a composition that could allow liquid oceans on the surface. Spectroscopic analysis revealed not just the presence of water vapor, but also its vertical distribution in the atmosphere. Models based on this data suggest that TOI 715b could have water clouds in its upper atmosphere, creating an evaporation and condensation cycle similar to Earth's, but operating under different conditions of gravity and stellar irradiation. One of the most exciting aspects of atmospheric analysis is how it reveals dynamic processes in real time. Some exoplanet atmospheres change dramatically on timescales we can observe, a matter of hours or days. HD 80606b, for example, has a highly elliptical orbit that takes it from very far from its star to very close in a matter of days. During this approach, its atmosphere heats up by more than 10 degrees Celsius, creating global storms we can detect through changes in its infrared emission. It's like having a natural laboratory for studying extreme meteorology, observing how atmospheres respond to drastic energy changes in real time. These studies help us understand not just these alien worlds, but also the fundamental processes that govern all planetary atmospheres, including our own. The search for atmospheric biosignatures, gases that indicate life, is becoming increasingly sophisticated. Molecular oxygen, as we mentioned, is an obvious candidate. But there can be false positives where non-biological processes produce oxygen. Phosphine, controversially detected on Venus, is another gas that on Earth is associated almost exclusively with life. But perhaps the most convincing biosignatures would come from combinations of gases that could hardly coexist without active biological processes. Oxygen and methane, for example, react chemically with each other. Their simultaneous presence in significant quantities would suggest that both are being constantly replenished, possibly by biological processes. Imagine the moment when we first detect an unambiguous combination of biosignatures in the atmosphere of a rocky exoplanet in the habitable zone. It would be a moment that divided human history into before and after, before knowing we're not alone and after. How do you think humanity would react to such a discovery? There's an almost musical beauty in the organization of our solar system. Small rocky planets close to the sun, gas giants in the outer regions, everything orbiting in an orderly and predictable fashion. For centuries, we assumed this would be the standard architecture for planetary systems. But the universe, as we've discovered, is a much more creative composer than we imagined, creating cosmic symphonies and arrangements that challenge our understanding. Have you ever contemplated what it would be like to live on a world where 2 or 3 suns shine in the sky? Where seasons are determined not by axial tilt, but by the complex orbital patterns of multiple stars. Where the very concept of day and night takes on completely new meanings. Approximately half of all stars in the Milky Way exist in binary or multiple systems, 2 or more stars, orbiting around each other in complex gravitational dances. For a long time, astronomers questioned whether planets could form and maintain stable orbits in such chaotic environments. The answer, revealed by exoplanet discoveries in recent decades, is a resounding yes, and the resulting worlds are more diverse and fascinating than any science fiction ever imagined. Kepler 1/6b was the first confirmed planet orbiting a binary star system, a real world that orbits 2 suns, like the mythical Tatooine from Star Wars. But unlike the arid desert of fiction, Kepler 1/6b is a cold gas giant, similar to Saturn, where surface temperatures are well below freezing. Still, its existence proved that planets can form and survive in binary star systems. Imagine being on the surface of a moon of Kepler 1/6b, looking at a sky where 2 suns of slightly different sizes perform a cosmic dance. During part of the day, you would see both suns in the sky, creating double shadows and unique light patterns. At other times, only one sun would be visible, or they might be so close in the sky that they would appear almost like a single elongated sun. The sunsets on such a world would be spectacles beyond imagination. Sometimes one sun would set while the other remained high in the sky. Other times, both would set almost simultaneously, creating a double twilight with colors that changed constantly as the 2 stars of slightly different temperatures disappeared over the horizon. But Kepler 1/6b is just the beginning. The universe has created even more exotic planetary architectures. Some planets orbit only 1 star in a close binary system, experiencing dramatic variations in irradiation as the companion star approaches and recedes during its orbit. Others orbit both stars simultaneously, like Kepler 1/6b, in orbits that take them through zones of drastically different temperature. HD 131,399 AB represents perhaps the most extreme case discovered so far, a planet orbiting one of the stars in a triple star system. Depending on the time and orbital position, this world can have 1, 2, or 3 suns visible in the sky simultaneously. Its year lasts 550 Earth years, during which it experiences seasonal patterns that have no parallel in our experience. Can you imagine the seasons on this world? During part of its 550-year orbit, the planet receives constant light from at least 1 sun, Essentially a summer that lasts decades followed by an equally long winter when all three stars are on the opposite side of the sky. Civilizations on such a world would develop completely different concepts of time, calendars, and even mythologies from ours. The detection of planets in multiple star systems has also revealed unique atmospheric phenomena. Planets orbiting close binary stars experience periodic changes in stellar irradiation that creates superseasons, dramatic climate changes occurring on much shorter timescales than orbital changes. HAP-1b, a hot Jupiter in a binary system, shows evidence of atmospheric waves that change direction dramatically as irradiation varies due to the movement of its companion star. It's as if the planet has two different weather systems that regularly alternate, creating meteorological patterns of unimaginable complexity. But perhaps the most intriguing worlds are those that orbit in the habitable zone of multiple star systems. Kepler 47c is a Neptune-sized planet orbiting two stars in the system's habitable zone. Although it's probably a gas giant, any substantial moon it might have could experience conditions suitable for liquid water. Imagine a habitable moon of Kepler 47c. During part of its orbit around the planet, it would experience normal days and nights as it rotated. But periodically, the planet would pass in front of one or both stars, creating eclipses that could last hours or even days. These planetary eclipses would create cycles of light and darkness completely different from anything known on Earth. Life on multiple star worlds would face unique challenges, but also unique opportunities. Photosynthesis could evolve to take advantage of different light spectra from various stars. Organisms could develop complex circadian rhythms synchronized with multistellar patterns of light and darkness. Intelligent cultures would develop incredibly sophisticated astronomies out of necessity, having to navigate skies where multiple stars create complex motion patterns. The architecture of multiple planetary systems also teaches us about planetary formation. Planets in such systems need to form in protoplanetary disks disturbed by the gravity of multiple stars. The fact that they not only form but can maintain stable orbits for billions of years suggests that planetary formation processes are more robust and adaptable than we thought. Some of the most stable systems appear to be those where planets orbit very close to one of the stars, S-type configuration, or very far from both, P-type configuration. The intermediate regions tend to be too chaotic for long-term stable planetary orbits. This has important implications for habitability. Planets in S-type orbits can have relatively stable climates if they're sufficiently close to a dominant star. Planets in P-type orbits may experience extreme, seasonal variations as their orbit takes them closer to or farther from the binary stellar pair. The discovery of planets in multiple star systems has also dramatically expanded our estimate of the total number of habitable worlds in the galaxy. If half of all stars are in multiple systems, and many of these systems can host habitable planets, then the potential number of worlds where life could arise is even greater than our most optimistic estimates based only on single-star systems. There are also fascinating implications for future interstellar travel. Multiple star systems offer potential multiple stops for expanding civilizations. A species that developed interstellar travel could establish outposts on different components of a multiple system, creating communication and trade networks that take advantage of complex stellar orbits. Have you ever wondered what it would be like to grow up on a world where the night sky is never truly dark? Where multiple stars create constantly changing patterns of light and shadow? How would this affect our perception of the cosmos, our philosophy, our art? The discovery of multistellar worlds forces us to expand our imagination about the possibilities of conscious experience in the universe. There exists a special type of melancholy that accompanies great astronomical discoveries, the simultaneous realization of how magnificent the universe is and how limited our capabilities are to explore it directly. Each exoplanet we discover is simultaneously a door that opens to new worlds and a reminder of the vast distances that separate us from them. When we contemplate direct exploration of exoplanets, we face numbers that challenge not just our current technology, but perhaps the very limits of physics. Proxima Centauri b, our closest exoplanetary neighbor, is 4.24 light-years away. To give you perspective on this distance, if we could travel at the speed of our fastest current rockets, it would take us about 73,000 years to get there. Even if we could accelerate a spacecraft to 10% of the speed of light, a technological feat that is far beyond our current capabilities, it would still take more than 40 years to reach Proxima Centauri, and that's just our closest neighbor. Most of the interesting exoplanets we've discovered are hundreds or thousands of light years away. There's something profoundly human about our frustration with these limitations. We're an exploratory species shaped by millions of years of migration across continents, oceans, and eventually to nearby space. Discovering thousands of potentially habitable worlds and not being able to visit them is like being a 15th century explorer discovering new continents through a telescope, but without ships to reach them. But perhaps this limitation isn't permanent. Humanity has a remarkable history of overcoming obstacles that seemed insurmountable. Just a century ago, traveling faster than sound seemed impossible. Just a few decades ago, instant global communication was science fiction. Perhaps interstellar travel is just the next impossible that we'll learn to overcome. Several conceptual proposals exist for interstellar travel. Giant solar sails could be propelled by powerful Earth-based lasers, accelerating small probes to significant velocities. The breakthrough Starshot project, which we mentioned earlier, proposes sending thousands of nanoprobes the size of computer chips to Alpha Centauri, each weighing only a few grams but carrying tiny cameras, sensors, and transmitters. Imagine receiving the first images of Proxima Centauri be transmitted by one of these nanoprobes. Even if they were just a few pixels showing variations in color and brightness, they would be the first direct photographs of a world outside our solar system. We could see if the planet has an atmosphere, oceans, perhaps even patterns suggesting geological or biological activity. Other proposals are even more ambitious. Nuclear fusion engines could, theoretically, accelerate larger spacecraft to substantial velocities. Bussard ramjet engines could collect interstellar hydrogen during flight, using it as fuel for continuous acceleration. More speculatively, if physics permits, concepts like Alcubierre drives could warp spacetime, allowing faster-than-light travel without violating relativity. But even if we overcome the technical challenges of propulsion, there are additional obstacles to interstellar travel. The space between stars isn't empty. It contains dust, gas, and cosmic radiation that would become dangerous to objects traveling at high speeds. A dust particle hitting a spacecraft traveling at 10% of the speed of light would have the energy of a small bomb. There are also human and social challenges. A journey to even the closest exoplanets would take decades or centuries with conceivable technologies. This would require generation ships, closed habitats where multiple generations would live and die during the journey. How would we maintain social cohesion and purpose during such long voyages? How would we preserve knowledge and technology across generations of space travelers? Perhaps more realistic in the short term is sophisticated robotic exploration. As our telescope technology continues advancing, we may be approaching capabilities almost equivalent to direct exploration for some purposes. The next space telescope after James Webb may be able to detect not just exoplanet atmospheres, but also surface features, weather patterns, and perhaps even unambiguous signs of life. Imagine future telescopes so powerful they could create detailed maps of continents on nearby exoplanets. We could see oceans, mountains, forests, if they exist. We could detect the lights of alien cities during their nights. We could observe seasonal changes, migration patterns of life, perhaps even signs of agriculture or technology. In some ways, this remote exploration may be superior to physical visitation for answering the most important questions. After all, our primary curiosity about exoplanets isn't necessarily to step on their soil, but to know if they host life. And that question may be answerable through spectroscopic analysis of their atmospheres and long-term observation of their activity patterns. There's also the intriguing possibility that alien civilizations face the same limitations we do. If interstellar travel is truly difficult, even for technologically advanced species, then the galaxy may be full of isolated civilizations, each exploring the cosmos through telescopes, each wondering if it's alone in the universe. This raises fascinating questions about interstellar communication. If we can't easily travel between stars, perhaps we can communicate. Radio messages travel at the speed of light, still slow in cosmic terms, but much faster than any conceivable spacecraft. The SETI Search for Extraterrestrial Intelligence project has been listening for signals from alien civilizations for decades. So far, we haven't detected anything definitive, but this may simply reflect the vastness of space and the difficulty of knowing where and how to look. If alien civilizations are sending signals, they may be using technologies or frequencies we haven't thought to monitor. Conversely, some scientists have proposed that we should send our own messages to the stars. But this raises complex ethical questions. Should we announce our presence to the cosmos, or is it wiser to remain silent until we know more about the nature of other civilizations? It's a decision that affects all of humanity, but who has the right to make it? There's also the possibility that the limitations of interstellar travel are, ironically, beneficial for the development of life and intelligence. If civilizations could easily travel between stars, perhaps a single dominant species would have colonized the entire galaxy long ago, preventing the independent development of other forms of life and intelligence. The vast interstellar distances may be what allows the universe to be a laboratory of diversity, where countless experiments in biological and cultural evolution occur in isolation, creating a richness of life forms and consciousness that would be impossible in a more connected cosmos. Have you ever considered that our current inability to travel to other worlds may be temporary, just a brief phase in the long history of our species? If humanity survives and continues advancing technologically for thousands or millions of years, perhaps the limitations that seem absolute today will become mere historical inconveniences. But even if we never develop practical interstellar travel, the remote exploration of exoplanets is already transforming our understanding of the universe and our place in it. Each new world discovered expands the realm of the possible. Each atmosphere analyzed refines our understanding of habitability. Each planetary system studied reveals new diversity in cosmic architecture. Perhaps the true exploration that matters isn't physical, but intellectual and spiritual. Through telescopes and scientific analysis, we've already visited thousands of distant worlds in our imagination and understanding. These journeys of the intellect may be ultimately more valuable than any physical journey. Throughout this journey through exoplanets and their wonders, we've danced around a question that resonates at the deepest core of human existence. Are we alone? This ancient question, which has tormented philosophers and scientists for millennia, is finally within reach of a definitive scientific answer, although perhaps not in the way we imagined. The search for life on exoplanets isn't just about finding little green men or advanced technological civilizations. It's a much more subtle and profound investigation into the fundamental processes that create and sustain life in the universe. And the clues we're looking for are often almost imperceptible chemical whispers in the atmospheres of distant worlds. When we think about biosignatures, chemical signals that indicate life, we tend to focus on gases like oxygen and methane, but the reality is much more nuanced. Life on Earth produces thousands of different chemical compounds, many of which could be detectable in planetary atmospheres if we knew to look for them and had sufficiently sensitive instruments. Consider, for example, the dimethyl sulfide, DMS, we mentioned earlier. On Earth, this compound is produced almost exclusively by marine phytoplankton microscopic organisms that form the base of many oceanic food chains. The detection of DMS on K2-18b was exciting precisely because it's very difficult to explain its presence through purely geological or chemical processes. But biosignatures can be even more subtle. Phosphine, a compound of phosphorus and hydrogen, caused scientific furor when it was controversially detected in Venus's atmosphere. On Earth, phosphine is produced by anaerobic bacteria, organisms that live without oxygen in environments like swamps and animal intestines. In an oxidizing atmosphere like Venus's, phosphine would decompose rapidly unless it was being constantly replenished. The controversy over Venusian phosphine perfectly illustrates the challenges of interpreting possible biosignatures. Detecting a compound is just the first step. Understanding its origin requires careful analysis of all possible processes that could produce it. In science, extraordinary claims require extraordinary evidence, especially when it comes to claims about extraterrestrial life. This is where exoplanet analysis becomes truly fascinating. Unlike Venus, which we can study with probes and landers, exoplanets must reveal their secrets entirely through the light they emit or reflect. Each photon we detect from an exoplanet carries encoded information about conditions on that distant world. The James Webb is revolutionizing our ability to decode these luminous messages. Its spectroscopic sensitivity allows detection of gases in concentrations that were undetectable just a few years ago. More importantly, it can detect multiple gases simultaneously, allowing more sophisticated analyses of chemical disequilibria that may indicate life. For example, the coexistence of oxygen and methane in an atmosphere is highly suggestive of life, because these gases react with each other. For both to exist in significant quantities, something must be constantly replenishing them, and biological processes are the most likely explanation for such simultaneous replenishment. But life may be even more creative than we imagine. On Earth, we find organisms in environments we once considered completely inhospitable: acidic hot springs, deep caves isolated from sunlight for millions of years, environments with radiation levels that would be lethal to most life forms. This extreme diversity suggests that life may exist in forms and places we haven't even thought to look for. Imagine silicon-based life forms instead of carbon-based ones, thriving on worlds with temperatures that would vaporize any terrestrial organism, or organisms that evolved to use ultraviolet radiation or cosmic rays as energy sources instead of sunlight. Such life forms would produce completely different biosignatures from those we currently seek. There's also the possibility of subsurface life on exoplanets. Many worlds that appear completely inhospitable on their surfaces may have subsurface oceans heated by radioactive decay or tidal forces. Such life would be almost impossible to detect through atmospheric analysis, but may be the most common form of life in the universe. The question of intelligent life is even more complex. SETI continues its silent search for signals from technological civilizations, but so far the cosmos remains mysteriously quiet. This could be because intelligent life is extremely rare, or because advanced civilizations use communication technologies we don't know how to detect. Or perhaps there's something about the nature of advanced intelligence that makes it naturally quiet. Very advanced civilizations may transcend the need for electromagnetic communication, developing technologies that don't produce detectable signals. Or they may deliberately avoid announcing their presence, considering the cosmos a potentially dangerous place. There's also the disturbing possibility that intelligence is a self-destructive phenomenon. Perhaps technological civilizations tend to destroy themselves shortly after developing interstellar communication capabilities, creating only brief windows of detectability before disappearing. But let's consider a more optimistic possibility, that life, including intelligent life, is relatively common in the universe. But we simply haven't yet developed the tools or wisdom to detect it. We're still in the early stages of our ability to study exoplanets. The James Webb, revolutionary as it is just the first of a new generation of telescopes that will transform our understanding of distant worlds. Future telescopes like the proposed HABEX, Habitable Exoplanet Observatory, will be able to detect and characterize rocky planets in the habitable zone of hundreds of nearby stars. They'll have the sensitivity to detect not just obvious biosignatures like oxygen, but also more subtle combinations of gases that may indicate biological processes. Imagine the moment when we detect our first unambiguous biosignature on an exoplanet. How would humanity react to confirmation that we're not alone in the universe? Would it be a moment of global celebration, or would it create anxiety about our uniqueness and cosmic importance? Paradoxically, even not finding life could be equally significant. If we study hundreds of potentially habitable worlds and find no signs of life, this would suggest that life is extremely rare, making our existence even more precious and meaningful. There are also fascinating ethical questions about how we should react if we detect extraterrestrial life. Do we have any responsibility to protect alien ecosystems? If we eventually develop interstellar travel capabilities, what rights would less advanced civilizations have to be left alone? The search for life on exoplanets is just beginning, but it's already transforming our perspective on our place in the universe. Each world studied, each atmosphere analyzed, each possible biosignature detected brings us closer to answering the deepest question we can ask: are we alone? Regardless of the answer, the very search is revealing a universe of diversity and possibility that surpasses our wildest imagination. And perhaps that's in itself a sufficient answer to our cosmic loneliness, the realization that we live in a universe so vast and full of worlds that life, in some form, almost certainly exists somewhere out there. There's a temporal dimension to the search for exoplanets that we rarely fully contemplate, the almost incomprehensible timescale over which planetary processes unfold. When we observe an exoplanet today, we're seeing a snapshot of a world that has billions of years of history and will continue evolving for billions of years in the future. It's like trying to understand a complex symphony by hearing only a single note. The formation of a rocky planet in the habitable zone is just the first movement of this cosmic symphony. What comes after the evolution of its atmosphere? The development of oceans, the possible emergence of life, unfolds on timescales that challenge human comprehension. Our species has existed for only about 300,000 years, a cosmic blink compared to Earth's 4.5 billion years of history. When we study young exoplanets, we see worlds still in the process of formation. Their protoplanetary disks are still coalescing, their atmospheres still being shaped by violent processes of accretion and bombardment by comets and asteroids. It's like observing cosmic babies taking their first steps on the journey toward planetary maturity. HL Tauri, a young star system just 450 light-years away, offers a fascinating window into these initial processes. Images from ALMA, Atacama Large Millimeter Array, reveal concentric rings in the disk of dust and gas around the young star, direct evidence of planets forming in real time. We're literally watching the birth of worlds, seeing how gravity sculpts the raw material of the cosmos into planets. But planetary formation is just the beginning. A planet's long-term evolution, its ability to maintain an atmosphere, develop stable oceans, and perhaps host life, depends on a myriad of factors that unfold over billions of years. The presence of a stabilizing moon, the strength of the planetary magnetic field, the rotation rate, the activity of the host star, all these factors influence habitability in ways that only become apparent on geological timescales. Our own Earth offers a fascinating example of this long-term evolution. The planet we see today is radically different from the primitive Earth. 4 billion years ago, our atmosphere contained no free oxygen and was composed mainly of methane, ammonia, and other gases that would be toxic to current complex life. The oceans were very different in chemical composition, and Earth's rotation itself was faster. A day lasted only about 6 hours. Earth's transformation from a hostile world to an oasis of life was a gradual process that involved what scientists call the Great Oxygenation Event. About 2.4 billion years ago, primitive cyanobacteria began performing photosynthesis, releasing oxygen as a waste product. Initially, this oxygen was absorbed by dissolved iron in the oceans, creating the banded iron formations we see today in ancient rocks. Only when this iron sink was saturated did oxygen begin to accumulate in the atmosphere. Have you ever paused to consider that the air you breathe right now is the product of billions of years of biological activity? Each oxygen molecule was produced by a photosynthetic organism, a plant, an alga, or a bacterium, at some point in Earth's long history. Our planet is literally a living world breathing. When we apply this temporal perspective to the exoplanets we've discovered, we realize we're seeing these worlds at random moments in their long evolutionary histories. A planet that appears inhospitable today may have been habitable in the past, or may become habitable in the future. Conversely, a world that seems perfect for life today may be heading toward a climate catastrophe that will make it uninhabitable in a few million years. Mars offers a poignant example of this temporal variability. Geological and atmospheric evidence suggests that ancient Mars had a thicker atmosphere, warmer temperatures, and liquid water flowing on its surface. Rivers carved valleys we can still see today, and oceans may have covered much of the planet's northern hemisphere. But over billions of years, Mars lost most of its atmosphere, probably due to its weaker gravity and lack of a strong magnetic field to protect it from the solar wind. If aliens had observed our solar system 3 billion years ago, they might have concluded that Mars was the most promising world for life, not Earth. This reminds us that our assessment of exoplanet habitability is necessarily limited to a snapshot in time. We can't see their past histories or predict their futures with certainty. Stellar evolution adds another fascinating temporal dimension. Stars are not constant. They evolve over billions of years, gradually becoming brighter as they age. Our Sun, for example, was about 30% less luminous when Earth formed. Paradoxically, this means that the primitive Earth should have been a frozen world based solely on the solar energy received, but geological evidence shows that Earth had liquid oceans even then. This faint young sun paradox was resolved by understanding that the primitive Earth had a much thicker atmosphere, rich in greenhouse gases that kept the planet warm despite the lower solar luminosity. As the sun became brighter, Earth's atmosphere evolved, with carbon dioxide levels gradually decreasing to maintain stable temperatures. This delicate dance between stellar evolution and atmospheric evolution determines the long-term habitability of any planet. Worlds that are on the outer edge of the habitable zone today may become more habitable as their stars become brighter. Conversely, planets on the inner edge may eventually become too hot to maintain liquid water. Venus may represent Earth's future. Some models suggest that Venus may have had oceans in the past, but as the sun became brighter and Venus's atmosphere developed a runaway greenhouse effect, those oceans evaporated completely. In about 1 billion years, the sun will be bright enough to cause a similar fate for Earth, unless our atmosphere evolves in ways we don't yet fully understand. But long-term planetary evolution isn't deterministic. It's influenced by random events that can drastically alter a world's trajectory. Large asteroid impacts can reset climatic evolution, massive volcanic eruptions can alter atmospheric compositions, and even the close passage of other stars can disturb planetary orbits. The impact that created the Moon about 4.5 billion years ago is a dramatic example of how unique events can shape long-term habitability. Without that impact, Earth might not have a large moon to stabilize its axial tilt, resulting in chaotic climate variations that could have prevented the development of complex life. When we study exoplanets, we're essentially sampling this vast landscape of evolutionary possibilities. Each world we discover represents a different natural experiment in planetary formation and evolution, each with its own unique history of success or failure in maintaining habitable conditions. Some exoplanets we study may be in their Archean eras, early periods when life is just beginning to emerge and transform their atmospheres. Others may be in equivalents to our Cambrian period, when complex life is rapidly diversifying. Still, others may be in advanced phases of planetary evolution, perhaps even beyond what Earth will experience in its future. The detection of biosignatures on exoplanets must be interpreted within this temporal context. A strong biosignature may indicate a world in the fullness of life, but an absence of biosignatures doesn't necessarily mean a planet is dead. It may just be in a different phase of its evolution, before life emerged or after it became extinct. This temporal perspective also has profound implications for our search for intelligent life. Technological civilizations may exist for relatively brief periods in a planet's history, perhaps only thousands or millions of years, before destroying themselves, evolving beyond detectability, or simply losing interest in interstellar communication. If civilizations have limited windows of detectability, then the probability of two civilizations existing simultaneously and being able to communicate becomes very small, even if intelligent life is relatively common. It's like two ships passing in the cosmic night, each transmitting signals for brief periods at different moments in galactic history. Have you ever contemplated what it would be like to observe an exoplanet's evolution and fast forward? To see billions of years of atmospheric change, surface evolution, and perhaps emergence and extinction of life compressed into a few hours? It would be like watching the complete biography of a world, from its violent birth to its eventual old age and death when its star expands to become a red giant. This temporal perspective reminds us of the impermanence and preciousness of habitable worlds. Earth won't be habitable forever. In about 5 billion years, the sun will expand to become a red giant, making our planet uninhabitable long before eventually engulfing it. But 5 billion years is an almost inconceivable time, enough for biological and perhaps technological evolution to take directions we can't even imagine. Perhaps the most profound lesson of the temporal perspective in exoplanet astronomy is patience. The universe operates on timescales that make our human lives instantaneous, but also offers possibilities for change and transformation that extend far beyond our individual existence. Each exoplanet we study is a reminder that we're part of a much larger cosmic story, a narrative that began billions of years before we were born and will continue billions of years after we're gone. There's a fascinating paradox at the heart of our search for exoplanets. The more we discover about other worlds, the more we learn about ourselves. Each distant planet we study functions as a cosmic mirror, reflecting aspects of our own existence and forcing us to question fundamental assumptions about life, intelligence, and our place in the universe. When we contemplate the extraordinary diversity of exoplanets, lava worlds where iron reigns, gas giants with diamonds floating in their atmospheres, rocky planets orbiting two stars, we're confronted with a profound realization. Earth is not the standard model for planets. We're just one possibility among countless others, a specific experiment in the vast cosmic laboratory of planetary formation. This realization is simultaneously humbling and liberating. Humbling because it forces us to abandon any notion that we're the center of the universe or the final purpose of cosmic creation. Liberating because it dramatically expands our sense of the possible, showing us that the universe is much more creative and diverse than our limited experience could suggest. Consider how our definition of habitability has evolved as we've discovered more exoplanets. Initially, we looked for planets exactly like Earth, the same size, at the same distance from sun-like stars with atmospheres similar to ours. But each new discovery has expanded our understanding of where and how life can exist. Slightly larger rocky planets than Earth, the super-Earths, may actually be more habitable than our own world. Their greater gravity allows them to retain denser atmospheres for longer periods, offering better protection against cosmic radiation. Their greater geological activity can keep plate tectonics active for longer, regulating climate through the carbon cycle. Worlds orbiting red dwarf stars, initially considered inhospitable due to intense stellar radiation, may be perfectly habitable if they have thick enough atmospheres to redistribute heat between their day and night hemispheres. Planets in binary or multiple star systems may experience complex seasonal patterns that create unique ecological niches for life's evolution. Each expansion of our definition of habitability forces us to re-examine our own circumstances. Why does Earth have exactly the size it has? Why does our solar system have the specific architecture we observe? Are these factors necessary for life or simply historical coincidences that shaped our particular evolution? The discovery that planets are extremely common in the universe, with estimates suggesting at least one planet per star in the Milky Way, represents a conceptual revolution as significant as Copernicus's revelation that Earth orbits the Sun. We're not just one planet among many in our solar system. We're one world among hundreds of billions in our galaxy, which is one among trillions of galaxies in the observable universe. But does this numerical vastness make our existence more or less significant? If there are trillions of worlds out there, some inevitably similar to Earth, does this diminish our cosmic importance or amplify it? One perspective suggests we're insignificant, just a grain of sand on an infinite beach. Another perspective argues that our ability to contemplate this vastness, to study other worlds, to ask questions about our own existence, is extraordinary regardless of how common life might be. The search for atmospheric biosignatures on exoplanets also forces us to confront the nature of life itself. What really constitutes life? Is our carbon and water-based definition universal, or does it simply reflect the only forms of life we know? If we discover silicon-based life forms or organisms that thrive in liquid methane, would this expand our understanding of ourselves as living beings? There are also profound psychological and philosophical implications to exoplanet discovery. Carl Sagan's pale blue vision, the image of Earth as a small point in the immensity of space, gains additional dimensions. When we consider that there may be millions of other blue dots scattered throughout the galaxy, each potentially hosting their own stories of life and perhaps intelligence. This perspective can generate both existential anxiety and cosmic wonder. Some may feel lost in the vastness, questioning whether their individual lives have any meaning on such a grand scale. Others may find comfort and inspiration in the idea that we're part of something much larger than ourselves, participants in a cosmic story of increasing complexity and emerging possibility. The possibility of intelligent life on other worlds raises even deeper questions about the nature of consciousness and our cosmic responsibility. If there are other civilizations out there, how might they have solved problems we still face: war, inequality, environmental degradation? What could we learn by observing not just abiological worlds, but possibly worlds inhabited by intelligent beings? Or perhaps we're unique in our particular form of self-aware consciousness, our ability to do science, create art, and contemplate the meaning of our own existence. Even if life is common, intelligence capable of studying exoplanets may be extraordinarily rare, making our cosmic perspective precious regardless of our galactic population. The technology we've developed to study exoplanets is also transforming our ability to understand our own world. Atmospheric analysis techniques developed to characterize distant worlds are being applied to monitor climate change on Earth. Planetary evolution models help us predict the long-term future of our own planet. Ironically, our search for other Earths is making us more aware of the uniqueness and fragility of our current Earth. Each exoplanet we study, whether a suffocating lava world or a distant ice giant, reminds us how precious the conditions that allow complex life to flourish on our world are. This perspective has important practical implications for how we treat our planet. If habitable worlds are rare and precious in the universe, then our duty to protect and preserve Earth's habitability becomes even more urgent. We are possibly the guardians of something extraordinarily rare and valuable in the cosmic context. The search for exoplanets is also influencing our art, literature, and collective imagination. Each new world discovered adds details to our mental atlas of the cosmos, offering scenarios for future stories of exploration, encounter, and perhaps communication with other forms of life. Have you ever imagined what it would be like to grow up in a civilization that has known about thousands of other worlds since childhood? How would this influence psychological development, philosophical perspectives, and the aspirations of a species? We're creating the first human generation that will grow up knowing with certainty that we live in a universe full of worlds. Perhaps the most important discovery to emerge from our search for exoplanets isn't about other worlds, but about ourselves. We are a species capable of detecting planets hundreds of light years away, of analyzing their atmospheres through light that traveled across the interstellar void, of imagining what it would be like to step on their alien soils. This capacity to transcend our physical limitations through science and imagination may be our most distinctive characteristic in the cosmos. Regardless of how many other worlds exist out there, regardless of how many other forms of life may have evolved, we are definitively a species that looks at the stars and sees possibilities. And so we arrive at the end of our contemplative journey through distant worlds, but not at the end of the questions they awaken. As you sit there, perhaps feeling the silent weight of night around you, or the soft light of an approaching dawn, I invite you to pause and reflect on everything we've explored together. We began this evening asking about worlds similar to Earth, and discovered that the universe is simultaneously more familiar and stranger than we ever imagined. There are worlds out there that could be incredibly similar to ours: rocky planets with liquid oceans, breathable atmospheres, perhaps even life flourishing under alien suns. But we've also discovered realities that challenge our imagination: planets where glass rains, worlds illuminated by multiple stars, atmospheres composed of vaporized metals. Through our most advanced telescopes, we've developed the extraordinary ability to chemically analyze worlds we can never physically visit. We can detect water vapor in the atmosphere of a planet hundreds of light years away, discern weather patterns on alien worlds, and even search for chemical signatures that could indicate life. The Kepler Space Telescope taught us that planets aren't rare, they're absolutely common, with estimates suggesting there are more planets than stars in our galaxy. The James Webb is now revealing the intimate secrets of these distant worlds, decoding the chemical messages written in light that crosses their atmospheres. We've learned about our immediate cosmic neighborhood, where Proxima Centauri b orbits the closest star to the Sun, offering a tantalizing destination for future robotic missions or perhaps even human exploration in centuries to come. We've explored the complexities of the habitable zone, discovering that habitability is much more nuanced and diverse than a simple matter of distance from a star. We've confronted the humbling limitations of interstellar travel, the vast distances separating us from these fascinating worlds, but also glimpsed future technological possibilities that could eventually take us to the stars. More immediately, we've recognized that our telescopes are already time machines, allowing us to explore other worlds through analysis of light that carries stories from distant planets. We've contemplated the search for extraterrestrial life, from microbes that could leave detectable chemical signatures in planetary atmospheres to possible intelligent civilizations that remain mysteriously silent in our search for signals of their existence. Each discovery brings us closer to answering the ancestral question, are we alone? We've reflected on the enormous timescales over which planetary processes unfold, recognizing that each exoplanet we observe represents a snapshot of a billion-year history. Some worlds may be just beginning their journeys toward habitability, while others may be in the final phases of their habitable eras. And through it all, we've discovered that the search for other worlds is, paradoxically, a search to understand ourselves. Each exoplanet we study forces us to re-examine our assumptions about life, habitability, and our place in the cosmos. We are simultaneously humbled by the vastness of the universe and elevated by our unique capacity to contemplate it. Now, as our journey together comes to an end, I want you to know that the discoveries we've shared tonight are just the beginning. The science of exoplanets is exploding with new revelations almost daily. New worlds are being discovered, new techniques are being developed, and our understanding of the cosmos is evolving in real time. Future telescopes promise even more extraordinary capabilities. We may eventually detect not just the presence of life on other worlds, but perhaps even specific characteristics of alien biospheres. We may map continents and oceans on nearby exoplanets, observe seasonal changes in real time, perhaps even detect the lights of alien cities during their nights. But regardless of what specific discoveries await in the future, one thing remains constant: our capacity to wonder, to question, to seek understanding beyond ourselves. This fundamental curiosity, this need to look at the stars and imagine, may be our most distinctive characteristic as a species. Do you remember when I asked, at the beginning of our journey, where you were and how you felt? Now, after everything we've explored together, how do you feel about your place in this vast cosmos populated by countless worlds? Is there something comforting in knowing that somewhere out there may be other blue worlds orbiting other stars, perhaps even other beings looking at their own starry nights and wondering if they're alone? Earth remains, as far as we know, the only world where life certainly exists, the only planet where consciousness emerged to contemplate its own cosmic existence. This makes our world infinitely precious, not despite the existence of other worlds, but because of them. We are part of a much larger story, participants in a cosmic narrative of increasing complexity and emerging possibility. When you look at the night sky in the coming weeks and months, remember that among those stars exist real worlds. Some may be similar to Earth, with oceans reflecting alien skies and atmospheres that could sustain life. Others are so exotic they challenge our imagination. All are part of the same universe that gave us birth. All are our cosmic companions on this journey through space and time. The search for Earth-like exoplanets continues, and each discovery brings us closer to answering the deepest questions we can ask about our existence. But perhaps the most important discovery has already been made: the realization that we live in a universe full of worlds, rich in possibilities where the story of life and consciousness is still being written. Thank you for accompanying me on this journey through distant worlds. Your presence, your curiosity, your openness to the marvelous made this exploration possible. May you carry with you the sense of wonder we've shared, and may you continue looking at the stars with eyes full of possibility. And now, as our formal journey comes to an end, I leave you with a final question to carry in your dreams and future reflections. If intelligent life exists on other worlds, looking at their own stars and asking the same questions we ask, what does this mean about the nature of consciousness, curiosity, and the universal impulse to understand our place in the infinite cosmos?